So we will be starting with a quadcopter drone design for a 5 kg drone. So we are designing a 5 kg quadcopter maintaining a 2:1 thrust to weight ratio principle. But notice how we have reached a critical threshold in professional applications. At 5 kg total weight, this platform can carry professional cinema cameras, sophisticated surveying equipments or meaningful cargo payloads of up to 2 kilograms beyond the drone's base weight. This capability opens commercial applications with real economic value. However, this weight class brings significant responsibilities. First, regulatory considerations. In many jurisdictions, drone over 2 kg face stricter regulations requiring operator certifications, registrations, and potential insurance. Second, safety imperatives. A 5 kg drone falling from a 50-meter carries the kinetic energy of a ball falling from the same height. Safety systems aren't optional, they are mandatory. Professional standards. At this investment level, typically $3,000 to $8,000 for a complete systems. Client expect professional reliability, comprehensive documentation, and proven performance. This isn't a hobby project, it's a professional tool that must perform reliably in commercial equipments. So we go for a required thrust calculation. Our systematic approach continues, but notice how the number reveals the scale of engineering challenges we are addressing. Total drone weight 5 kg, force required to lift is equal to mass into gravity, that is mg, that is equal to 5 kg into 9.81, that is equal to 49.05 newtons. With a proven 2:1 thrust to weight ratio, total thrust required is equal to 2 into 49.05 newton, that is 98.10 newtons. So we can approximate it to 100 newtons. For our quadcopter configuration, thrust per motor is equal to 100 Newton divided by 4, that is equal to 25 Newtons per motor. Converting this to gram forces, 25 Newton is equal to 25 Newton divided by 9.81 into 1000 grams, that is equal to 2550 grams of thrust per motor. Let's pause and appreciate this requirement. Each motor must produce 2550 grams of thrust, 5 times what a 1 kg drone required. This isn't just scaling, this represents a fundamental shift in motor technology and propeller aerodynamics. At this thrust level, we are dealing with significant aerodynamic forces and vibrations, substantial electrical current and heat generation, critical structural loads on motor mounts and frame, propeller tip speeds approaching aerodynamic limits. This thrust requirement drives us into a completely different category of components, industrial grade motors designed for professional applications with expectations of thousands of flight hours. So next we go for the motor selection. Motor selection at 2550 gram thrust per motor reveals fundamental principles about how electric propulsion scales to larger systems. We now target brushless motors in the 400 to 550 kV range, dramatically lower than even our 3 kg designs, that is 700 to 900 kV range. This isn't arbitrary, it's dictated by propeller physics and motor efficiency principles. Why ultra low kV would be a question. So yes, lower kV motors provide higher torque at lower RPM, essential for turning the massive 16 to 18-inch propellers required for efficient thrust at this scale. Think of it like gear ratios in vehicles. Heavy trucks use lower gear ratios for maximum torque, exactly as we use lower kV motors for heavy lift applications. Notice our efficiency factor has decreased further to 6.5 grams per watt. This continuing decline in efficiency as we scale up reflects fundamental physics. First, larger motors have increased electromagnetic losses. Second, higher power densities generate more heat. Third, mechanical losses scale unfavorably with size. Fourth, larger air gaps in magnetic circuits reduce efficiency. The power calculation per motor would be power required is equal to 2550 grams divided by 6 grams per watt, that is equal to 392.3 watts per motor. This is substantial power, nearly 400 watts per motor, totaling almost 1600 watts for the complete system at maximum thrust. For comparison, that's more power than many household applications. Current calculation using 6S LiPo, that is 22.2 volts nominal. Maximum thrust current is equal to 392.3 watts divided by 22.2 volts, that is equal to 17.67 amperes per motor. Cruise current at 80% throttle is equal to 17.67 ampere into 0.8, that is 14.14 amperes per motor. Peak current is equal to 17.67 into 1.5, that is 26.51 amperes per motor. This current level required serious electrical engineering. At 26.5 amperes, a poorly designed controller or undersized wire generates significant heat. Wire gauge selection, connector quality, and solder joint integrity become critical engineering considerations. The 6S battery selection is essentially mandatory at this scale. Higher voltage reduces current requirements, minimizing resistive losses and heat generation throughout the power distribution system. The next is ESC selections, that is electronic speed controls. The ESC selection at this power level transitions from component selection to thermal engineering. Our peak current per motor is 26.51 amperes with a 30% safety margin. Required ESC rating is equal to 26.51 ampere into 1.3, that is equal to 34.46 amperes minimum. I recommend 35 to 45 ampere ESCs, and here's why. This seemingly excessive margin is actually engineering prudence. Thermal management is critical. At these current levels, I square R losses, that is the heat, generate substantially heat. A 35 ampere ESC running at 26.5 ampere is operating at 76% capacity, generating manageable heat. The same ESC at 90% capacity would likely enter thermal protection or fail. Heat generation follows I square R. As current increases, heat increases quadratically. The difference between 30 ampere and 40 ampere ESC isn't just 33% more capacity, it's dramatically reduced operating temperature and extended service life. Professional reliability standards. ESC failures in 5 kg drones have serious consequences. First, potential injury from falling drone. Second, property damage from crash. Third, loss of expensive payload equipments. Fourth, possible legal liability. The cost difference between 35 ampere and 45 ampere ESC is perhaps $20 per unit. The cost of a single crash easily exceeds about $1,000. This is risk management through engineering design. Advanced feature required. Professionally, grade ESC in this range provides a real-time telemetry for current, voltage, and temperature monitoring. Second, active thermal protection preventing catastrophic failure. Third, superior electromagnetic interference shielding. Fourth, firmware updates for performance optimization. Fifth, BSC, that is battery eliminator circuit capable of powering multiple accessories. At this scale, ESC selection isn't just about current rating, it's about system integration and reliability engineering. So we move on to the next component, that is the battery, and we will look upon for the battery calculation for a 5 kg drone. Battery sizing for 5 kg drone involves complex trade-offs between flight time, power delivery capability, weight constraints, and safety requirements. Flight time target 15 minutes, that is 900 seconds. Notice, we have reduced the flight time from 20 minutes in a 3 kg drone. Why? Because power requirements scale unfavorably and maintaining long flight times would require prohibitively heavy batteries. The current drawn calculations per motor at cruise is equal to 14.14 amperes. Total for 4 motors is equal to 56.56 amperes. So for 900 seconds it would be 56.56 amperes into 900 seconds, that is 50,904 ampere seconds. Converting it, 50,904 divided by 3,600, that is 14.14 ampere hours, that is 14,140 mAh. With 80% discharge depth, required capacity is equal to 14,140 mAh divided by 0.8, that is equal to 17,675 mAh. Weight budget, 14% of total weight, that is equal to 2000 grams maximum. This is where engineering becomes challenging. A 6A 18,000 mAh LiPo battery typically weighs 1800 to 2200 grams. We are at the absolute limit of our weight budget. Battery selection strategy. Practical choice. 6x LiPo 13,500 to 18,000 mAh capacity. Why this range rather than a specific number? 13,500 mAh, lighter option, approximately 100 grams, provides 12 to 13 minutes of flight time, allows heavier payloads. 18,000 mAh, heavier option, approximately 2100 grams, provides full 15 plus minutes, reduces payload capacity. This flexibility is intentional. Professional applications require mission-specific optimization. Photography missions might prioritize longer flight time, cargo delivery prioritizes payload capacity. Now we move on to the C rating considerations. So at 56.56 amperes, that is continuously drawn, a 15,000 mAh battery requires C rating of 56.56 amperes divided by 15 Ah, that is equal to 3.77 C continuous. Most professional batteries are rated between 25 to 35 C continuous, providing substantial margin. However, verify manufacturer specifications. Some manufacturers overstate C rating significantly. Battery management systems. At this investment level, proper battery management isn't optional, it's mandatory. Balance charging for cell health, voltage monitoring per cell during flight, temperature monitoring during operation, proper storage voltage maintenance, that is 3.8 volt per cell, cycle count tracking for preventive replacement. So a 6S 16,000 mAh LiPo battery costs around $200 to 400. Proper management extend life from 100 to 150 cycles to 300 to 500 cycles, saving 1000 over the platform's lifetime. Now we go to the next component, that is the propellers. Propeller selection at this scale involves aerodynamic engineering principles that become dominant factors in performance. For 400 to 550 kV motors on 6S battery, optimal size is 16 to 18 inches in diameter with 5 to 6 inches of pitch. These are serious propellers with significant aerodynamic complexity. Aerodynamic considerations. Tip speed limitations. At 16 to 18-inch diameter, propeller tips travel at high velocities. Let's calculate. 18-inch propellers, that is 0.457 meter diameter and 0.229 meter radius. Motor at 8880 rpm, that is 400 kV into 2.2 volt. Tip velocity is equal to 2 pi r into rpm per 60, that is equal to 2 pi r into 0.229 into 8880 divided by 60, that is 213 milliseconds. This approach is 0.1 Mach, beginning to encounter capacitive effects that reduce efficiency and generate noise. This is why ultra-low kV motors are essential. They keep propeller RPM low enough to avoid these limits. The Reynolds number factor. At this scale and velocity, propellers operate at Reynolds number around 1 lakh to 2 lakh, where aerodynamic efficiency is higher but sensitive to surface finish and profile accuracy. Manufacturing qualities matter significantly. First would be the pitch selection strategy. 5-inch pitch, maximum efficiency for hovering applications, lower power consumptions, quieter operations. The 6-inch pitch, higher powered speeds for mapping or survey, faster cruise speeds, increased power consumptions. Material engineering. Carbon fiber consideration is absolutely mandatory because it has a structural strength to withstand centrifugal forces exceeding 100 gram at tips. The stiffness to prevent flexing that reduces efficiency. Durability for thousands of flight cycles. Balanced construction to minimize vibration. The safety considerations. An 18-inch carbon fiber propeller spinning at 8000 rpm carries tremendous kinetic energy. Catastrophic failure could cause serious injury. Quality propellers include factors balancing to plus minus 0.5 grams, stress testing for crack detection, manufacturing quality control, recommended replacement schedules. Never use propeller beyond their rated service life or after any impact. The next would be the frame considerations. Frame engineering at 5 kg scale requires structural analysis principles typically reserved for aerospace applications. Frame size must accommodate 16 to 18-inch propellers requiring motor-to-motor diagonal of 650 to 900 mm. This is a substantial physical structure, nearly a meter in diagonal dimension. The target weight is around 750 to 850 grams, that is 15 to 17% of the total weight. So, what is the structural engineering requirements for this? Load analysis. The frame must withstand multiple simultaneous load. Static loads 5 kg weight plus 2 kg payload. Dynamic loads 2 grams of maneuvering forces. Thrust loads 2550 gram per motor mount. Landing impact potentially of 400 to 500 grams or 343 newtons. The vibrational energy 100 to 150 Hz frequency from motors and propellers. The second is material selection. Carbon fiber is mandatory, but specific layer matters. Unidirectional carbon for arms, maximum length bending. Woven carbon from plates for providing multidirectional load distribution. Typical specifications 3K carbon fiber, twill width 400 gram. Design features required. First, vibrational isolation. Professional camera are sensitive to vibration. Required systems are rubber damper for flight control, isolate from 100 to 150 Hz motor vibrations. Anti-vibration mounting for camera gimbal, isolate from structural resonance. Balanced propellers plus minus 0.5 gram or better. Thermal management. ESC generating 40 to 50 watts of heat required. Airflow channels for natural convection cooling. Aluminium heat sinks on high power ESCs. Thermal insulation from battery compartment. The next is the cable management. At this scale, wire harness can exceed 50 conductors. So, it should be protected cable channel prevents propeller strikes. Strain relief prevents fatigue failures and segregation of power and signal wiring prevents EMI. The next is payload integration. Professional application required quick release payload mounting for rapid configuration. Standing mounting interferences, NATO rail, cold shoe mounts. Balance mounting to maintain center of gravity. Weather protection for sensitive equipments. Next is the landing gear. At 5 kg, landing forces are substantial. Retraceable gear for unobstructed 360-degree camera views. Shock absorption for 1 to 2 meter per second landing velocities. Sufficient ground clearance for gimbal and payload. And the last is modular design philosophy. Professional operation demands rapid arm replacement after crashes, accessible component replacement for maintenance, standardized connectors for quick repairs, and tool-free battery installation. This isn't a frame, it is an integral mechanical system designed for professional field operations. The next is the comparison between the theoretical and simulation comparison. Our validation table shows the refinement that comes from validating theoretical calculations with sophisticated simulation tools. The component comparison analysis is motor kV. In theoretically we get 400 to 550 and in simulation we have seen it is 400 kV. The simulation selected the lower end for the maximum efficiency and optimal propeller matching. This reveals an important principle when uncertain, error towards lower kV for better efficiency and motor longevity. ESC ratings. It lies between the range of 35 to 45 in the theoretical calculations, while in simulation we get it around 40 amperes. The simulation chooses the mid-range, balancing the cost with thermal margin. This represents professional grade components with adequate headroom. Now it comes the battery capacity. 13,500 to 18,000 mAh theoretically, but in simulation the simulation chooses the lower end, that is the 13,500 mAh, prioritizing weight savings over maximum flight time. This suggests payload capacity was valued over endurance, a legitimate engineering trade-off. The next is the propeller size. It's around 16 to 18 inch theoretically, and in simulation we get it around 15 inch. Interesting divergence. Simulation selected slightly smaller propellers. Possible reasons could be better throttle response with lower propeller inertia, reduced tip speed for noise reduction, more margin for frame size constraints, trade efficiency for maneuverability. The frame size 650 to 900 mm theoretically. On the other hand, the simulation chooses it at 670 mm. That is near the minimum value of the range, optimizing for compact design while maintaining structural integrity and adequate propeller clearance. The next is engineering insights. The simulation consistently choose conservative, efficiency-focused options. This reflects professional design priorities: reliability over performance, efficiency over power, longevity over capability. This validation process is essential. It reveals where theoretical calculation leave room for optimization based on specific mission requirements. So after getting a comparison between the theoretical and the simulation results, we can get that almost of our theoretical calculation matches with the simulation result, and there is a slight difference between them. The next is engineering principles used, or the summary of overall engineering principles used during the drone design. The fundamental engineering principles remains consistent, but the application at 5 kg scale reveals why professional drone design demands engineering expertise. First is the current calculation logic. Ohm law remains a foundation, but notice how voltage selection becomes critical. At these power levels, even small improvements in efficiency translate to significant practical benefits. 1% efficiency improvement is equal to 8 watts saved. 8 watts is equal to reduced heat, extended component life, improved reliability. Design standard evaluation. 2:1 thrust to weight ratio. Still optimal, but at this scale provides just adequate maneuverability. Some professional platforms use 2.5:1 for improved wind resistance and faster climb rates. 80% battery discharge limit. Even more critical, deep cycling a $300 battery shortens its life dramatically. Protecting that last 20% saves thousands over the platform's lifetime. Then is the motor, that is 6.5 gram per watt efficiency. Reflects real reflects reality of large motors. Understanding this declining efficiency helps predict real world performance versus theoretical calculations. Next is the 30% ESC safety margin. At 26.5 ampere peak current, this margin prevents thermal issues that would ground the platform during critical missions. The next is 40% weight allocation for battery. This percentage has remained remarkably consistent from 1 kg to 5 kg, suggesting it represents a fundamental optimum in electric aircraft design. The new engineering principle at 5 kg scale. System integration complexity. At this scale, the interaction between subsystems becomes as important as individual component specifications. Flight controller must integrate with gimbal control systems, telemetry and video transmissions, GPS and navigation systems, autonomous flight systems, safety and redundancy systems. The next is thermal engineering. No longer optional, 1600 watts total power means significant heat management challenges throughout the system. Regulatory compliance. Many jurisdictions require specific design feature for drones over 2 kg, including redundant flight control systems, automated safety features, remote identification capability, and geofencing implementation. Professional documentation. Commercial operation requires component traceability, maintenance records, flight logs, performance documentation, and safety procedures. This isn't just engineering, it's system engineering with professional responsibilities. The next we will look up for required safety features. At 5 kg, safety system transition from optimal enhancement to mandatory requirements. Let's examine why each system is essential. The first is redundant power distribution system. Why critical? A single point of failure in power distribution causes catastrophic system failure. Professional systems include dual battery capability with automatic failover, redundant voltage regulators for flight critical systems, protected power distribution preventing single point failures, current monitoring on each power rail. The next is motor failure detection and compensation. Modern flight controllers can detect motor failure through unexpected attitude changes, current anomalies, reduced control authority, ESC telemetry feedback. Upon detection, the system can compensate using remaining motors, execute control emergency landing, alert operator of failure mode, and log failure data for analysis. The next is automatic return to home capabilities, essential for beyond visual line of sight operations, which are triggered by signal loss, low battery, or operated command. GPS-based navigation to launch point, obstacle avoidance during return, automated landing sequence, position hold if landing zone obstructed. The next is geofencing support, prevents operation in restricted airspace, preloaded no-fly zone databases, real-time airspace updates via cellular connection, altitude limitation based on location, virtual boundaries for operational safety. The next is low battery automated landing. Critical safety feature prevents mid-air power loss, which can lead to conservative voltage monitoring per cell, tide warning systems, power reserve calculation based on altitude and distance, automatic landing site selection using vision systems, emergency landing procedures. For critical failures, control descent maintaining attitude control, a reduced descent rate for minimal impact, auto rotation attempts for propulsion failure, emergency position logging for recovery. Some additional professional systems include redundant flight controller, dual flight controller architecture with independent sensor systems, automatic failure capability, and cross-checking for fault detection. The next is parachute recovery system. For catastrophic failures, ballistic deployment for rapid activation, sizing that is descent rate less than 5 meter per second for 7 kg total weight, automatic deployment triggers, free fall detection, altitude loss. The next is position lighting required for visibility and orientation. FAA compliant anti-collision strobes, orientation lights that is the red starboard, green port and white aft. Higher intensity LEDs visible to 5 plus kilometers. And the last is telemetry and the black box. Professional operations required. Complete flight data logging, GPS track recordings, altitude, speed and altitude logging, battery performance recording, event logging for incident investigation. These aren't features, they are engineering requirements for possible operations for a 5 kg aerial platform. The next we will see the applications for a 5 kg drone. Let's examine the professional applications that justify the sophisticated engineering we have designed into the platform. Professional cinematography with heavy camera systems. 5 kg platforms can carry cinema grade cameras, RED Komodo, BMP-CC 6K professional 6K cinema cameras, high-end gimbal systems providing 360 unrestricted movement, professional lens systems for cinematic focal lengths, real-time video transmission for director monitoring. This isn't drone photography, it's aerial cinematography meeting Hollywood production standards. The next is payload delivery, that is up to 2 kg additional capacity. Commercial delivery applications may be medical supplies to remote locations or emergency equipment to disaster areas, parts deliver for industrial operations or just sample transport for laboratories. The 2 kg payload capacity makes this economically viable, enough capacity for meaningful cargo while maintaining safe flight characteristics. The next is industrial inspection with specialized equipment. Professional inspection systems, thermal imaging cameras, ultrasonic thickness measurement, gas detection centers, and high resolution zoom cameras for detailed inspection. Applications include power line inspection, bridge and infrastructure inspection, solar farm inspection, and industrial facility inspection. The next is agricultural applications. Precision agriculture is required, multispectral cameras for crop health analysis, NDVI sensor for vegetation monitoring, RTK GPS for centimeter level accuracy, and spray systems for targeted applications. The next is search and rescue operations. Life-saving applications, thermal imaging for person detection, communication relay systems, emergency supply delivery, rapid area scanning, and night vision capabilities. Scientific research and data collection, academic and research applications such as environmental monitoring, wildlife tracking and observation, atmospheric sampling, geological survey, and archaeological site documentation. Each application has their specific requirements that us systematic design methodology can address through mission specific optimization. And hence we come to the conclusion of this 5 kg drone design. Like we have engineered a completely sophisticated 5 kg professional quadcopter that represents the pinnacle of what can be achieved with standard quadcopter designs. Beyond this weight class, we will need to consider hexacopter or octocopter designs for redundancy and safety. The systematic methodology we have applied, from basic thrust calculations through sophisticated systems, demonstrate that professional drone design is rigorous engineering requiring expertise across multiple disciplines: aerodynamics, electrical engineering, structural engineering, and system integration. This 5 kg platform represents a $5,000 to 8,000 investment with capabilities that can generate substantial commercial value. The engineering rigor we have applied ensure reliability, safety, and performance worthy of professional applications. Thank you.